Welcome to Unacademy Computer Science. This is GATE Umamaheshwar Rao. Unacademy GATE and ESE presents Major League Combat on June 26th at 11 a.m. Guaranteed scholarship on participation. Top rankers to win up to 90% scholarship. Enrollment is free. Attention Unacademy GATE and ESE aspirants, get iconic subscription for an additional 555 rupees per month. Live classes by top educators, 8,000 plus printed and digital notes per branch, unlimited access to record content, priority in raise a hand and ask a doubt features. Interactive live classes, polls for the learners, raise a hand option, never miss a class, lecture notes, anytime, anywhere. Attend live classes, participate in the live quiz at any time, anywhere. Daily scholarship test. Unacademy is conducting daily scholarship test. Grab this opportunity to win great scholarship daily. Community feature for Android that facilitates educator and learner connect even outside the classroom. Unacademy GATE subject wise PYQs, practice for GATE and ESE with Unacademy PYQs. Enroll now. Unacademy is announcing droppers batch for GATE and ESE 2023. Droppers batch for GATE 2023. Use code KUR75. Unacademy is announcing droppers batch for GATE 2024. Use code KUR75. Nothing can stop you from chasing your GATE and ESE dream. Get started with 0% EMI today. Benefits of 1:1 live mentorship program. Unacademy GATE and ESE iconic subscription. Scheduled session as per your convenience. Exam and preparation guidance, progress report available to mentor for tracking learner activity. Unacademy is congratulating GATE 2022 top 6 rankers. Unacademy is congratulating ESE 2021 mechanical top rankers. The features of Unacademy subscriptions: top educators, doubt clearing sessions, study notes, test series in both plus and iconic subscriptions. Physical notes, 1:1 live mentorship program, strategy and study program, live audio interaction during open house, only on iconic subscribers. Either for plus subscription or iconic subscription, use code KUR75. Yesterday I have discussed relations: a reflexive relation, irreflexive relation, symmetric relation, asymmetric relation, antisymmetric relation, and transitive relation. Now, counting relations. Counting relations. If cardinality of A is n, then cardinality of A cross A is n square. Sir, if cardinality of A is n, then cardinality of A cross A is n square. Now, if cardinality of A is n, then number of relations on A, number of relations on A is given by 2 power, please observe, number of relations on A is nothing but number of subsets of A cross A. Number of subsets of A cross A is 2 power n square. Therefore, the total number of relations on A is nothing but 2 power n square. Next one, number of reflexive relations on A. Number of reflexive relations on A. Observe here, 1, 2, 3 and so on n. N plus 1, n plus 2 and so on n square. Now observe, reflexive relation means for every A belongs to A comma A must be in your relation. That's why it must contain 1 1, 1 1, 2 2, 3 3, n n. Sir, what about remaining? See, reflexive relation means if for every A belongs to A comma A must be in your relation. That's why these are compulsory, must be present. There is no other option. But for the remaining order pairs, may be present or may be absent. Remaining order pairs may be present or may be absent. Sir, how many remaining order pairs? Observe. First, n self pairs. Remaining are n square minus n. N order pairs must be present. Remaining n square minus n order pairs, for every order pair we have two choices, either present or absent. That's why total number of possible ways are, total number of reflexive relations on A are 2 power n square minus n. 2 power n square minus n. Because 1 into 1 into 1 n times gives you 1 power n, that is 1. But 2 into 2 into 2 n square minus n times, therefore 2 power n square minus n. That is nothing but 2 power n into n minus 1. Number of reflexive relations on A is nothing but 2 power n into n minus 1. Next, number of irreflexive relations. Number of irreflexive relations on A. Number of irreflexive relations on A. Total number of relations are n square. That's why I am taking n square blank places. First one, second one, third one, nth one, n plus 1th one, n squared one. Now 1 comma 1, 2 comma 2, 3 comma 3, n comma n. Observe, a relation is said to be irreflexive if for every A belongs to A comma A not belongs to R. So compulsory these self pairs should not be present. So this must be absent. This must be absent. This must be absent. This must be absent. So what about remaining? Either present or absent. Next one, either present or absent. Next one, either present or absent. So 1 into 1 into 1, how many times? N times. 1 power n. 2 into 2 into 2, how many times? N square minus n times, because total number of order pairs are n square, self pairs are n, so remaining are n square minus n. So 2 power n square minus n, 2 power n into n minus 1. Next one, symmetric relations. The number of symmetric relations on A. The number of symmetric relations on A. Observe, when we will say relation is symmetric, if A comma B belongs to R, compulsory B comma A should be in R. Observe, A comma B belongs to R, B comma A should be belongs to R. Now, I am going to take order pairs pairwise. First one, second one, nth one. So remaining order pairs are n square minus n, but I am taking pairwise. That's why by 2. Observe, 1 comma 1, 2 comma 2, n comma n. Now 1 2 2 1, 1 3 3 1, n plus 1 comma n, 1 minute, n minus 1 comma n, n comma n minus 1. I have taken 1 2 2 1, 1 3 3 1. I have taken pairwise. When you take pairwise, you have 4 possibilities. What are the 4 possibilities? Either 1 2 is present, 2 1 is present, 1 2 is absent, 2 1 is absent, 1 2 present, 2 1 is absent, 1 2 is absent, 2 1 is present. 4 possibilities. Out of 4 possibilities, how many possibilities are favorable to symmetric? Sir, if 1 2 is present, 2 1 is present, that is favorable. 1 2 is absent, 2 1 is absent, that is also favorable. Only 2 cases are favorable for symmetric. So 2 cases are favorable cases. That's why here 2 ways. In this case, 2 ways. In this case, 2 possibilities. In this case, 2 possibilities are favorable to symmetry. Sir, how many cases? N square minus n by 2 cases. Sir, what about self pairs? What about reflexive pairs? See, 1 comma 1 has 2 possibilities, either present or absent. 2 comma 2 has 2 possibilities, either present or absent. N comma n has 2 possibilities, either present or absent. So here 2 into 2 into 2, how many times? N times. That's why 2 power n into 2 into 2 into 2, how many times? N square minus n by 2 times. Now simplifying this, we get 2 power n into 2 power n square minus n by 2. A power m into a power n form, a power m plus n. That is 2 power LCM is 2, 2n plus n square minus n. That is 2 power n square plus n by 2, 2 power n into n plus 1 by 2, 2 power n into n plus 1 by 2. That is the correct answer. Next problem. Number of asymmetric relations on A. Number of asymmetric relations on A. Number of asymmetric relations on A. 1 1, 2 2, n n. 1 2 2 1, 1 3 3 1, n minus 1 comma n, n minus 1 comma n. 1 2 n. Observe here. I am taking remaining order pairs pairwise. 1 2 2 1, 1 3 3 1, n minus 1 comma n, n comma n minus 1. Observe here, these are all self pairs. 1 comma 1, 2 comma 2, n comma n. Now 1 comma 1 in asymmetric relation, self pairs should not be present, therefore this must be absent. 2 2 must be absent, n n must be absent. Sir, what about 1 2 2 1? Here we have 4 possibilities. 1 2 is absent, 2 1 is absent. 1 2 is present, 2 1 is absent. 1 2 is absent, 2 1 is present. Both are present. If both are present, that is not favorable to asymmetry. If 1 2 is absent, 2 1 is absent, favorable. 1 2 is present, 2 1 is absent, favorable. 1 2 is absent, 2 1 is present, favorable. So 3 cases are favorable to asymmetric. Both are present is not favorable. Now, here we have 3 favorable cases. Here 3 favorable cases. Here we have 3 favorable cases. So these are nothing but n square minus n by 2 because we have taken pairwise. So 1 into 1 into 1 n times is nothing but 1 power n. Multiplied with 3 into 3 into 3, how many times? N square minus n by 2 times. Three power n square minus n by 2. Therefore, 3 power n into n minus 1 by 2. 3 power n into n minus 1 by 2. So the total number of asymmetric relations on A equal to 3 power n into n minus 1 by 2. Next one. Number of anti-symmetric relations on A. Number of anti-symmetric relations on A. One two two one, 1 3 3 1, n minus 1 comma n, n comma n minus 1. N reflexive pairs, remaining are, I have taken pairwise, that's why total number of relations are n square. Now if you subtract reflexive pairs n square minus n, we have taken pairwise, that's why divided by 2. Self pairs 1 1, 2 2, n n. See, In the case of antisymmetric relation, reflexive pairs may be present or may be absent. So two possibilities. Two possibilities. Here also two possibilities. Next. So what is antisymmetric? If A comma B belongs to R, B comma A belongs to R, A must be equal to B. Now I have taken pairwise. So here we have four possibilities. 1, 2 is absent, 2, 1 is present. 1, 2 is present, 2, 1 is absent. 1, 2 is absent, 2, 1 is absent. 1, 2 is present, 2, 1 is present. So if both are present, A must be equal to B, 1 must be equal to 2. That is not favorable. How many are favorable? Only 3 cases are favorable. Okay na? 1, 2 is present, 2, 1 is absent. 1, 2 is present, 2, 1 is absent. 1, 2 is absent, 2, 1 is present. 1, 2 is absent, 2, 1 is also absent. These 3 cases are favorable. Three favorable cases. Observe here. Here also 3 are favorable. Here also 3 are favorable. So 3 into 3 into 3. How many times? 3 into 3 into 3. How many times? N square minus n by 2 times. 2 into 2 into 2. How many times? 2 power n. Therefore, 2 power n into 3 power n square minus n by 2. So, the final answer is 2 power n into 3 power n square minus n by 2. The number of antisymmetric relations on A is equal to 2 power n into 3 power n square minus n by 2. Next one. The number of reflexive and symmetric. Reflexive and symmetric. The number of reflexive and symmetric. Observe here. One one, two two, n 1221, 1331, n minus 1 comma n minus 1 comma n. Total number of order pairs are n square. So, total number of order pairs are n square. I am taking pairwise. That's why I have to write n square minus n by 2. This is 1 comma 1, 2 comma 2, n comma n, 1 2 2 1, 1 3 3 1, n minus 1 comma n, n comma n minus 1. Observe. Now reflexive. Reflexive means compulsory. 1 comma 1 must be present. 2 comma 2 must be present. N comma n must be present. So 1 into 1 into 1, how many times? N times. Therefore 1 power n. I have taken pairwise. That's why here we have 4 possibilities. 1 2 is present, 2 1 is also present. 1 2 is absent, 2 1 is absent. 1 2 is present, 2 1 is absent. 1 2 is absent, 2 1 is present. Now, out of these 4 cases, how many are favorable to symmetry? Both are present and both are absent are favorable to symmetric. Favorable to symmetric. Therefore, here 2 cases are favorable. Here 2 cases are favorable. Similarly, here 2 cases are favorable. So 2 into 2 into 2, how many times? 2 into 2 into 2, how many times? N square minus n by 2 times. 2 power n square minus n by 2 times. That is 2 power n into n minus 1 by 2. 2 power n into n minus 1 by 2. The total number of reflexive and symmetric relations on A are 2 power n into n minus 1 by 2. Now, properties. Let R, R1, R2 be the relations on A. Be the relations on A. Let R, R1, R2 be the relations on A. Now, observe the table. I am going to give total 18 properties in this table. R inverse, R1 intersection R2, R1 union R2. R inverse, R1 intersection R2, R1 union R2. Now, reflexive, irreflexive, symmetric, symmetric, asymmetric, anti-symmetric, transitive. Observe here. If the relation R, R1, R2, If R is reflexive, R inverse is also reflexive. If R is irreflexive, R inverse is also irreflexive. If R is symmetric, R inverse is also symmetric. If R is asymmetric, R inverse is also asymmetric. If R is antisymmetric, R inverse is also antisymmetric. If R is transitive, R inverse is also transitive. Next, R1 and R2 are reflexive. R1 intersection R2 is reflexive. R1 and R2 are irreflexive. R1 intersection R2 is irreflexive. R1 and R2 are symmetric. R1 intersection R2 is symmetric. R1 and R2 are asymmetric. R1 intersection R2 is asymmetric. R1 and R2 are antisymmetric. R1 intersection R2 is antisymmetric. R1 and R2 are transitive. R1 intersection R2 is also transitive. If R1 and R2 are reflexive, R1 union R2 is also reflexive. R1 and R2 are irreflexive, R1 union R2 is also irreflexive. R1 and R2 are symmetric, R1 union R2 is also symmetric. R1 and R2 are asymmetric, R1 union R2 is asymmetric. R1 and R2 are antisymmetric, R1 union R2 is also antisymmetric. R1 and R2 are transitive, R1 union R2 is also transitive. So here R1 and R2 are transitive, R1 and R1 union R2 need not be transitive. R1 and R2 are asymmetric, R1 union R2 need not be asymmetric. The meaning is need not be. Now, representing relations. How we are going to represent the relations? Representation of relations. Representation of relations. Let R be a relation on A. Let R be a relation on A. Let R be a relation on A. Then we are going to represent in two ways. One is matrix relation. One is matrix relation. Another one is digraph relation. In matrix relation, MR equal to Aij n cross n, where Aij equal to 1 if I comma j belongs to R, which is 0 if I comma j not belongs to R. What about digraph relation? If there is a relation, we are going to join the vertices with a directed line segment. If there is a relation, we are going to join with a directed line segment. For example, A is 1, 2, 3, 4. The relation R is 1, 1, 1, 2, 1, 4, 2, 2, 1, 1, 1, 2, 1, 4, 2, 2, 2, 4, 2, 1, 4, 2, 4, 3. Now, the matrix relation MR is the matrix relation MR is 1, 2, 3, 4. Now, 1, 1 belongs to R, therefore 1. 1, 2 belongs to R, therefore 1. 1, 3 not belongs to R, 0. 1, 4 in the relation, yes. 2, 1, 0. 2, 2, yes. 2, 3. Here, this is 3, 1, 3, 1. This is 3, 1. Now, 2, 3, 0. 2, 4, yes. 3, 1, yes. 3, 2, 0. 3, 3, 0. 3, 4, 0. 4, 1, 0. 4, 2, yes. 4, 3, yes. 4, 4, 0. That is matrix relation. When you represent by digraph, vertices 1, 2, 3, 4. Now, 1, 1, 1, 1. 1, 1 means you have to write self pair. Next, 1, 2. 1, 4. 2, 2. 2, 4. 3, 1. 4, 2. 4, 3. Understood? Next, closures. What is a reflexive closure? Reflexive closure on R. That is represented by RR. The reflexive closure is nothing but smallest reflexive relation containing R. Smallest reflexive relation containing R. Smallest reflexive relation containing R. Sir, how to get smallest reflexive relation containing R? For example, A is 1, 2, 3. Suppose the relation R is 1, 1, 2, 2, 2, 3, 1, 1, 2, 2, 2, 3. See, it is not reflexive. It is not reflexive. It is not reflexive because 3, 3 not belongs to R. That's why it is not reflexive. So how to get reflexive? Just you take union of delta relation. Simply you follow these 2 points. First point, if R is a relation on A, R is a relation on A, then the reflexive closure is given by R equal to R union delta. You just union with the delta relation. The given relation is R is 1, 1, 2, 2, 2, 3. If you union with the delta relation, now R equal to R union delta. Union. Delta relation is nothing but 1, 1, 2, 2, 3, 3. Now the resultant relation is 1, 1, 2, 2, 2, 3, 3, 3. For every A belongs to A belongs to A belongs to R. That's why it is reflexive closure. RR is given by R union delta. R union delta. Next. Suppose, second point. Suppose if R is reflexive, then if R is reflexive, then reflexive closure RR is nothing but R. If R itself a reflexive, then reflexive closure is nothing but R. Suppose if R is not reflexive, then you have to take union with delta. Automatically will get reflexive closure. Next. Symmetric closure. Symmetric closure of R. Symmetric closure of R. It is represented by RS. Now, the smallest symmetric relation containing R. Now, for example, A is 1, 2, 3. Now, the relation R is 1, 2, 2, 1, 2, 3. Verify whether R is symmetric or not. 1, 2 belongs to R, 2, 1 belongs to R. Okay, but 2, 3 belongs to R, but 3, 2 not belongs to R. Therefore, it is not symmetric. It is not symmetric. It will be symmetric if 3, 2 belongs to R. That's why what you have to do, please remember, if you would like to get symmetric closure, you have to take union with R inverse. So, now I am writing first point. If R is symmetric, then RS, I mean symmetric closure of R, is nothing but R. Suppose R is not symmetric, if R is a relation on A, then RS is equal to R union R inverse. Now, in this example, RS equal to 1, 2, 2, 1, 2, 3, union with R inverse. What is R inverse? 2, 1, 1, 2, 3, 2. That is R inverse. If you take union, you will get 1, 2, 2, 1, 2, 3, 3, 2. That is symmetric closure of R, RS. Understood? So if R is symmetric, symmetric closure of R is R. If R is not symmetric, R is some relation on A, then symmetric closure of R, RS is given by R union R inverse. So reflexive closure is given by R union delta relation. Symmetric closure is given by R union R inverse. Third one, transitive closure. Transitive closure. Third one. Transitive closure of R. Transitive closure of R, generally represented by R plus or R power infinite. Now, observe. Transitive closure, if R is transitive, definition is same, like smallest transitive, smallest transitive relation, smallest transitive relation containing R, smallest transitive relation containing R, results, first result, R is transitive, R is transitive if and only if R is equal to R plus. Number 2, R transitive closure of R is given by R union, R square union, R cube union, R power n. R power n. Actually here R square is nothing but R circle R. R cube is nothing but R square circle R. R circle R square. R power n is nothing but R circle R power n minus 1. So the union of R, R square, R cube and so on R power n is nothing but transitive closure of R. Transitive closure of R. Whenever you would like to find out transitive closure, either you have to apply Warshall's algorithm or digraph method. By using digraph method or Warshall's algorithm, we are going to write transitive closure of the given relation.